In this slide, we are going to learn about deep learning, how to do the deep learning in the text analytics. This is the agenda for our class in this week. We are going to learn about the RNN. What is RNN for the NLP? And the RNN as the language models. We are going to look at the NLP tests with RNN. And we are going to look at the RNN issues and variants. At the end, we are going to do the code analysis. We call it RNN, which is recurrent neural network. And we usually use the term vanilla. Vanilla means the basic or the original. Maybe if this is the algorithm, then the original algorithm. If this is a concept, then this is the original concept. Vanilla means the basic one of the recurrent neural network. And in the vanilla recurrent neural network, we have the format 1 to 1. It means we have one input, we are doing the process, and we have one output. Okay, one input, and we have one output. In the input, this is the X, this is the input, and there will be a kind of state, we call it H0, and we are going to process in the RNN using the recurrent neural network, and we are going to show the output, which is Y1. And then we will do next. After the first state completes, we go to the next state. The state refers to the H, and this is about the state 0, and then we have the state 1, and then we go to the next, which is the state 2, state 3, and so on. So the state number, it depends about the repetition. So if you have like 100 repetition, then the state will be until 100. So the steps in an RNN for the NLP. First, we need to initialize the hidden state, H0, and other parameters. When you see the figures before, we have the H0, or this is the initial state, the initial hidden state. Next, we are going to compute the hidden states, or the HT, for each input in the sequence. So T represent the state number 1, state number 2, state number 3, and so on. Optionally, compute outputs YT at each step. So optionally means it is optional if you want to get the output in the step, in every step, or at the final step. So we will check the variant of RNN later. Next is pass the hidden state from one step to the next. And then process the final hidden state or sequence of outputs as needed for the test. Finally, we will calculate the loss and apply back propagation through time. Okay, we will take a look also what is back propagation through time, or BPTT, to update the weight and the bias. So the RNN hidden state, we can process a sequence of factors. A sequence of factors X means we have the X1, X2, X3, and so on. by applying a recurrent formula. The recurrent formula means the formula that occurs every state, the formula that happens every time step. So the formula will be something like this one. When we are calculating the new state or HC, it means there will be a function of the numbers in the old state and also the value in the input. So the input factor at the time step. For example, if I want to know the HT, then I will like to know what is the old state and the current input. So this is the formula. HT or the current time will be obtained from the previous state with the current input. We can have another kind of function. We can have another kind of function to output the y. After we have the h, we can consider this h as the input to produce the y. So this is the output, and this is the new state. This is a function with the parameter w, or later on we can see this is as a weight. When we have a weight, then we can use this one to calculate what is the current hidden state to produce the output. So the vanilla recurrent neural network, it means that we need to understand the state. And now let's consider only a single hidden factor h. So let's consider only one. The hidden state ht is updated at its time step using the formula this one. So every time step we will update with this function, looking by the previous state with the current input. And then we will do, for example, we apply a tangent function. Okay, this is the tangent function. Then the new hidden state ht will be using the tangent function of the width multiplied by the ht minus 1 plus the width multiplied by the current input. And finally, y, or the output, is computed from the current hidden state. So it means we have the x, we have the h, and h will be combined with x in order to produce y. In overview, we can see the initial hidden state. After we have the function, this function is the function to combine the initial hidden state with the x1. After we have the result calculation, we will have the h1, and h1 will be the input for the next formula, for the next calculation. With this function, we will have the input, which is the h1 and x2, in order to produce the next state, which is h2, and then another calculation will be done to produce the h3 and so on. So the h2, x3 will produce h3 and so on until the t, until the time step t. We need to use the same weight, reuse the same weight matrix at every time step. Whenever we do this one, we have the result FW. Okay, we have the FW from the H0 and X1. So this W, it is the same width at this step. So we use the same W, the same W, the same W every time step. And after we finish, we will do the back propagation later. So yeah, that's how we do the R and N. As you know, the first we do the initialization on the hidden state and compute the HT and then compute the YT, pass the hidden state from one step to the next and process the final hidden state or sequence of output for the test. We will do this one later and we will check how to calculate the loss and how to apply the BPTT. So let's see some example how to calculate the the R and N. Let be the sequence is this one, I love NLP. So the vocabulary size, assume each word is encoded as a one hot factor. Do you know this one? One hot factor. It means if I have I love NLP, then I make the X1 as 100. It means this factor is for the word I, this factor is for the word love, and this factor is for the word NLP. The X1, because I'm referring to the word I, then it will be 100. The X2, because I'm referring to the word love, then it is 0, 1, 0. X3, this is for the word NLP, then the X3 is 0, 0, 1. Okay. So one more time, this is for the index on the word I, this is the index for the word love, and this is the index for the word NLP. We have 3 X for the representation. In order to calculate the weight, so let's say I have this weight. So usually we need to run some deep learning to get the weight, but sometimes we can get this initial weight. Okay, the initial weight is randomly generated, or in some of the algorithm they have the optimal weight parameters for the initial value. So let be this is the weight. We call it this is the W. So the W is this value, and then this is the W X. It means this is the weight matrix for the input to the hidden function. We have also another kind of weight matrix. We call it this is hidden to hidden, or this is the W. It's if you look at this one, W X then it means this is to compute from the X to its. This is W this is to compute from the X to the next state of X. For doing the neural network, there should be bias. If you join the data mining in the neural network, we can see there are some bias, and this is the bias value for the hidden state or X. And let be the initial hidden state is this value 0.0. Now, in order to do the R and N, okay, so we have this initial value. The H0 is the initial hidden state, and then we have the x, which is to compute from this x into the fw, and then we have the h, this is to compute from the h0 into the h1, and the calculation will be added with the bias. Now we can do the calculation. So for every word, it means if I'm now in the word I, then I can say this is in the time step 1. For the time step 1, then we do with the factor x1, which is 1, 0, 0. Then we can perform the calculation. Now let's suppose the function we are using tangent. So the function can be, you can use the sigmoid function or the logistic function. This function you can also perform the ReLU function and many things for function. But in this example, let me just perform the tangent function. This is tangent function. Tangent from the wxh multiplied by x1, okay, because I want to update the result on the h1. It means I need to get the x value into the function, and then I'm going to update the h0 with the width, which is the width hh. This is the width xh, and then at the end the function will be added with the bias. Then we just put the value from the original value in the previous page. When we do the wx, it's x1, it means this is the wxh multiplied by 1, 0, 0. You know the matrix multiplication. So we got the value 0.5 multiplied by 1. And then 0.8 multiplied by 0 minus 0.6 multiplied by 0. Then we got the value 0.5. For the second one, minus 0.3 minus 0 multiplied by 1, and then minus 0.2 multiplied by 0, and 0.4 multiplied by 0. So we got this value. Wait more. Is it this is the matrix 3 multiplied by 1, and this one is 1 multiplied by 3. I think this is why this one. I think I missed something here. If it is 3 multiplied by 1, and this one is 1 multiplied by 3, then it should be 3 multiplied by 3. Oh, let me check again this one. So I will do the next one. The h0. So the h0 is 0.0, which is the initial hidden state. The initial hidden state is 0.0. Then every value that multiplied by 0, it will be 0. Then the result is 0, 0. If we do with the all calculation, okay, so we got this value from here. So I will update later about this one. Plus 0.0, and then plus the bias. So the bias is from this 0.1, 0.1. Then we got the result 0.6 and 0.7. And we will do the tangent. the tangent function is a result from this one, and we got the value, the h1 is this value. So the updated h1, now we are going to use this one as the input for the next function. Okay, for the next function, it means we go to the time step 2. So time step 2, we are using the word love. So the word love, we use the 0, 1, 0. Again, we are doing the xh multiplied by x2, and then plus the whh multiplied by h1, which is the result from the previous states, plus the bias. Then yeah, we have this matrix multiplication. And after we got this one, we again multiply with the h1, with the status of h1. So this is the wh from the original, and we multiply with the h1. So we got this value. And then we do for the overall function. So we do the overall function. The result is this value. And after we have this value, again, we do with the tangent function. Okay. So the tangent function here is the tangent from this value. Tangent of 0.0784, tangent of 0.1991. Then the h2, now we have h2 as much as this one. Next, because we still have one word, which is the NLP, then we use the input factor, which is 0, 0, 1. Again, we calculate to get the h3, and we use the same tangent function, and this is the formula. We obtain the h3 equals to the x3 multiplied by the width of xh, and then we have this width multiplied by the whh plus the bias. So we get this one. This one is 0.5 multiplied by 0, and then 0.8 multiplied by 0, this multiplied by 0, and then this one multiplied by this one multiplied by this one, and this one multiplied by this one, in order to get this value. Maybe I will make some details to how to get this one later. And we have the value for the whh multiplied by h2. And then again, we do the multiplication for the whx with the x3. We do the multiplication of whh with h2, and we add the bias. Then we got this formula in order to get the final result. So after we got this final result, then again we do the tangent function. We do the tangent function, we got this value. So after we process the entire sequence, we have the hidden state. So we have what is h0, the initial, we have the h1, we have the h2, we have the h3. Then we have the h1, we have h2, and we have the h3. So this is the hidden state for every of this step. So after we have that hidden state, we will do the repetition. We will do the repetition. It means we will update the weight. So after we have this hidden state, after we have the H1, H2, H3, so we will do again updating the weight, updating the weight XH and updating the weight of its. Why we need to update this one? So at the end, we need to find the minimum loss. We need to check the minimum loss. The weight where the loss is minimum will be chosen. So if the minimum, if the loss already minimum, then we finish the repetition. So we call this is a recurrent approach because it will be repeated every time until we got the minimum loss. There are some variants on the RNN. Okay. When I show you the example, it is only for one sentence, like I love NLP. And the variance can be not only one-to-one, but it can be another variance like one-to-many. So one-to-many means there is one input, but the output can be more than one. For example, I have an image. So I give one picture, and then I want to know how to describe the picture. So the result will be a sequence of words. Or the other kind of example, let's suppose I ask the model to generate a sentence. Given an input, let's say I give the input sunny. So after I give the input sunny, the result will generate a sentence. Sunny day is beautiful and warm. So sunny day is beautiful and warm. It means from the input of one sentence, it will generate many sentences. The other kind of sequence, we can see the structure many to one. If the structure is many to one, means we have many input, and at the end, we have one output. So for example, you have a video. So there is a video, and the video, you usually split the video into some segment. So segment 1, segment 2, segment 3, or sometimes we call it frame. Frame 1, frame 2, frame 3. So from the frame 1 and frame 2 and frame 3, we will do something. We will do the modeling, and the model will predict whether it is an activity or whether it is a product or whether it is a view or whether it is an animal, and etc. So the output will be only one. In the text analytics, we can use for the sentiment analysis. For example, if the input is X, like the movie was absolutely brilliant and I love every minute of it, then there are many texts here. The output is only the sentiment, which is 1, positive. Then, yeah, we call this is many to one. The other kind of sequence we can see from many to many. If it is many to many, it means we have many input and we have many output. So many input means, for example, a sequence of video. So as I mentioned before, this is frame number 1. This is frame number 2. And this is frame number 3. So based on the information frame number 1, frame number 2, frame number 3, then we can produce an output, and the output will give you some kind of caption. So caption, maybe we can say this is a picture of maybe banana, something like this one. Then the caption is a sequence of words. So one word present this one word present this one word present this one, and so on. So it is many to many. The other kind of example in the text analytics, we can use the RNN for many to many. For example, if I give X, okay, the X is a sentence. The dog is happy. And then I want to translate it. Let's say the translation is from English to Spanish. Then the output is also many. For example, this one is the translation El perro está feliz. Then we have many words and at the input section, and we have many words at the output section. And the other kind of variance, we can have many to many, something like this one. It means once I input, when I give one input into the function, then there should be an output. Once I give an input, there should be an output. Once I give an input, there should be an output. So for example, we can do the video classification. If it is on the frame, so we have frame 1. What is the information on the frame 1? What is the information on the frame 2? What is the information on the frame 3? Or you can have like the pause thing. I don't know if you still remember. In the week 3 or in the week 2, we learn about the POS tagging. In the POS tagging means I want to know what is the word, whether like this one, the is a determiner. Then we can put the tag. This is a determiner. Cat is a noun. Then we put this as a noun. Set, it is a verb. On, it is a preposition. The is a determiner, and met is a noun. So every word, every input here, we have an output, and we are going to do this post tagging. I know that this is determiner, this is a noun, this is a verb, and so on. So we can use this RNN to do this prediction. After we do this prediction, after we have the X and we produce Y, we can calculate the loss. We can calculate L. So after we do the prediction on Y2, after we do the prediction on Y3 until Y3, then for every of this Y, we can check the loss. The loss means I want to know whether the prediction result is the same with the actual value or not. If they are the same, then there is no loss. If they are not the same, then there is a particular loss. So we can calculate the loss of L1, which is the loss from the prediction result at the Y1. We can also do the loss on the time step 2, which is the loss from the Y2, and so on. Then we can combine everything into big L. So the big L is the total loss. So LT means the loss at the specific time step. Okay, maybe I will stop here. So for the remaining, I will continue tomorrow. Okay, I will give you more details about the RNN in details and also the code by tomorrow. Okay, any questions?